benefit of our speaker, let me introduce a little bit about the Haki conference. So actually, Haki is the oldest civil engineering association in Indonesia, and our conferences are one of the most awaited and sought after conferences for our community. And we have this conference annually every year. However, during COVID, we were not able to hold it. So actually, 2022, this year is so special because finally we can come together again. So now, let me introduce you to give a brief introduction about our speaker today. Dr. Andrew Taylor is the technical director of KPFF Consulting Engineers in Seattle, where he is the lead design for special seismic systems, such as seismic isolation and seismic damping. He is also a specialist in seismic design of reinforced concrete structures, we like that, and has an experience of over 30 years in structural engineering. Not only that, Dr. Taylor has numerous technical committee experiences, both at the local and national level. What we know, of course, is that currently he is the chair of the American Concrete Institute 318 Building Code Committee, which will complete the next edition of the U.S. National Concrete Building Code in 2025. And other than that, he is also a member of the 2022 edition of the ASCE 7 Building Code. He has so many experiences. He has been part of the Applied Technology Council project, ATC 98, on the use of high-strength reinforcement for seismic design. And he was also the chair of the Earthquake Engineering Committee of the Structural Engineers Association of Washington. Dr. Taylor also serves as an affiliate professor in the Department of Civil and Environmental Engineering at the University of Washington, where he has enjoyed teaching courses in structural analysis and reinforced concrete design. So it is such a pleasure for all of us to welcome you here today with us, virtually, of course. Big applause to Andrew Taylor first.
Thank you.
So, Andrew, I hope you don't mind that I don't know where I should look at right now so that you can see me on the screen, but
I can see you.
We're there. So, let me give a brief introduction before we go to your presentation about what you are actually going to present today. So, Andrew Taylor, because of his credentials, is the perfect person for us to actually learn about ACI 31819. Today, in this short course, he is going to give an overview of changes in the ACI 31819 Building Code. But not just that, he also will give us like a looking ahead type of perspective of ACI 31825. So as we know, the first edition of the American Concrete Institute Building Code was actually published in 1910. However, it has consistently been reviewed and revised over the years, and especially between 2008 and 2014, they made a major a reorganization of the building code so that it will be easier to be used, which is now called the ACI 31819 and ACI 31819R. I'm sure everybody is very well knows about this. So today he will give us an introduction about what are the big major changes 31814 and then how it looks like right now in ACI 31819. And I heard here in the abstract I read that you will also give us a little bit of the process development of what will be the next edition of ACI 31825. Kalau bahasa Indonesia kita dikasih kisi-kisi 31825 nanti seperti apa ya. Okay, so without further addition, I will give the screen to you, Dr. Andrew Taylor. Please.
Thank you.
Start. Yes.
Let's see, I will share my screen, which, there we go. Do you see my presentation?
Hello? Yes,
Yeah,
we can
you
see
do.
your presentation.
Okay, wonderful. And question is, can you hear me all right?
Yes.
I just want to make sure you can see and hear me. So, okay, very good.
We can
So-
see and hear you.
Very good. Thank you for inviting me today. It's always a pleasure to be involved with this conference. I have attended this conference 2 times in the past before COVID, and I've very much enjoyed my time in Jakarta and also meeting new people. I see many familiar faces in the audience today. Perhaps someday in the near future, I will be able to return and speak in person. But again, thank you for inviting me. I will be speaking in English, and I wish I could speak in another language, but I express myself best in English. So I appreciate your listening to my presentation in English. I want to point out that the shirt I'm wearing was a gift from the conference organizers the last time I was in Jakarta. So I thought that in honor of that experience, I would wear this shirt today for my presentation. So thank you very much for that. All right, well, I think we'll get started. Here's the title slide, which simply tells you that I'm going to present ACI 318.19 and how it has changed between 318.14 and 318.19. And then since I'm chair of the current 318 committee, I will give you a little preview of what we think will be coming in 318.25. So I hope you find that interesting. So let me make one adjustment to my screen here for a moment. I'm going to move. Okay, I'll stay there. And I'm going to move my camera down so I can speak directly. Pardon me for this technical change. Give me a moment here. That way I can look more directly towards you. There we go. All right. Now I will also change this way. Okay. So I assume that you can see me now, and I can look at you more directly. Okay. So thank you very much for inviting me. As I said, I will be speaking, let me back up. I will be speaking for a little over an hour, maybe 90 minutes, and then we'll have time for questions. So I will attempt to answer as many questions as I can. The 2 main topics that I will talk about are the changes, as I mentioned, between ACI 2014 and ACI 2019. And then I'll be describing some of the changes, not all of them because we're still working on it, for the 2025 building code. I want to point out that in this presentation, there are a number of changes to ACI 318.14 to 19. But in this presentation, I will only cover the most important ones, the major ones. And I will let you know what these most important changes are. But normally when I present about the changes between ACI 318 and 14, it is about a 6-hour presentation. So I've condensed that and I'm going to cover the most important points today. I want to point out that since 2014, the ACI code has been organized into 10 sections, and you see them listed here. The first is general, which contains information on how the code is to be used and interpreted, and so on. And then loads and analysis, member strengths, joints and connections, seismic materials appears in a section, material and ductility, strength and serviceability, reinforcement, details, construction-related provisions, and evaluation of existing structures. This is just to give you a very large overview of how the code is organized. Now, I want to point out also that there are several editions of the code available, including one in SI units, which is the one that I'm assuming that you would be using. The one on the right is the inch-pound units version, the one that I use most. You can see the difference here is shown in the upper right corner, inch pounds versus SI. There are also editions of the code in Spanish, Chinese, and I believe one or two other languages. But most importantly, the slides that I'm showing you today are mainly listed in the American units or inch-pound units. However, I have attempted to translate those units in key points within this presentation into SI units. For instance, I've converted kilopounds per square inch, or KSI, into megapascals. I've converted forces into newtons, and so on. So hopefully you'll be able to follow along in familiar units. And I've listed also here, just for your convenience, the conversion factors if you wish to convert anything from the inch-pound version to the SI version. One factor I find very interesting is the very last one, pounds per square inch times 0.006895 is megapascals. And I wanted to note that that is the famous number associated with the secret agent James Bond, 0.007. So remember that number if you're ever converting from pounds per square inch to megapascals. All right, let's get started on the actual contents of the code. When it comes to repairing existing buildings, those that have been damaged or deteriorated, the code refers to the document ACI 562, which is a repair and rehabilitation. It's a very comprehensive and helpful code. So if you are encountering a situation where you need to repair an existing structure, please refer to that code. But we also say in ACI 318 that the provisions for new construction or new design can be used when repairing an existing structure. So if you're using ACI 562, you will also refer back to ACI 318, which is what we're talking about today. So I'll skip way to the end of the code. The very last chapter is chapter 27, and its topic is the strength evaluation of existing structures. This applies when a structure is completed and but hasn't been occupied yet. However, there may be some question about the strength of the structure, and this often happens if, for instance, a concrete test, strength test comes in that's too low. And so it may be necessary in some cases to evaluate the strength of an existing structure in order to certify it for occupancy. Now, what is generally well understood by engineers is to look at the structure that's in question, if perhaps the concrete strength is lower than expected, and perform calculations to evaluate that structure. I think many of us understand how to do that and to see if the lower strength is perhaps acceptable. But what is not well understood generally is the procedure for actually performing a load test on the structure in the field. And this load can be applied in a number of different ways with heavy blocks, with tanks of water, with hydraulic jacks, a number of ways. But there are two test procedures described in chapter 27. If you are encountering a situation where you need to actually test the strength of a structure, one procedure is called the monotonic test. It takes a long time because, as you can see in the lower graph, that you have to apply the load and hold it for 24 hours, so a full day, remove the load, and then evaluate the deflection after another 24 hours. So it takes at least 2 days to perform this test. There's an alternative procedure, which is called the cyclic procedure. That is presented in the document ACI 437. And as you can see, the total time for one test is 120 minutes or 2 hours, meaning that this test can be performed much more quickly, and perhaps several tests can be performed at different locations in a structure if necessary. It's a cyclic load test where the load is increased and then decreased, increased again, and so on. So I just want to make you aware of those testing procedures that are available in 318 and in ACI 437. All right, now we're going to go back to some of the more fundamental aspects of design that are covered in ACI 318. I want to point out something which is actually not new in the code, but it's very important, so I want to bring it up. In previous years, previous editions of the ACI code, let's say ACI 318-08, 2008, the loads in that code were based on a US document called ASCE 705. In that code, the wind loads that are specified in ASCE 705 are not factored, meaning when one is creating the load combinations for design, you have to multiply the wind load from ASCE 7 by 1.6. So it's a factored load in that case. Now, what has happened since then, not new, but in the last 3 editions of the ASCE 7 load document, that document has changed from service level loads to strength level loads. And the load factor used in load combinations is 1.0. So the wind loads as presented in ASCE 7 now are already factored. So it's a very important distinction to be made aware of for wind loading, because the difference is a factor of 60% for wind loads. So if you follow current practice and use factored loads in your design, whether they're from ASCE 7 or some other document, as long as they are considered strength level wind loads, then the load combinations in ACI 318 are correct. Okay, just a very important point about wind loading. Another aspect of concrete design that I'm involved with quite a lot is the vibration of floors, either for sensitive occupancies like medical MRI machines or electron microscopes, or for human comfort, such as in apartment buildings, offices, and so on, where occasionally floor vibrations can be a problem. Now, generally, concrete floors perform quite well from a vibration standpoint, and typically we don't have issues with them. However, there are cases, for instance, long spans, very high precision machinery, or where there's a rhythmic loading, such as an exercise studio or vibrating machinery, and sometimes precast concrete elements can exhibit vibration that is not acceptable in a particular situation. So in the commentary to ACI 318, there are references for procedures and methods that can be used to evaluate floor vibrations. And I want to point that out because occasionally that is something that just about every consulting engineer needs to deal with. All right, now we're going to talk about types of members, meaning slabs, beams, walls, and so on. The first type of member we're going to talk about is one-way slabs. So these are slabs that flex in one direction rather than in two directions. And of course, they're the simplest type of slab. With this type of slab, the one-way bending slab, we are concerned with all structural systems, but in particular this one, about the potential for collapse under extreme loads that are actually we don't even consider in our design. What we would like to do is to preserve the integrity, the structural integrity of these elements, these slabs in particular, so that they will remain in place. They may be severely damaged, but they will have a good chance of not collapsing. Because as we know, collapse causes of one element in a structure causes loads on adjacent elements. So we want to preserve this structure in its original configuration, even though it may be severely damaged. So there are new provisions in the ACI 318 code to provide very minimal, inexpensive, continuous reinforcement in the in one-way slabs to provide a high degree of confidence that they will remain in place if they are subjected to some very extreme loading that it wasn't anticipated in the original design loads. So that's what's new about one-way slabs. Not much has changed, except that there's those new provisions for integrity reinforcement. So regarding two-way slabs, you may be interested to see that two of the methods that have been in the code for a very long time, maybe, I don't know, 50 to 80 years they've been in the code. The direct design method and the equivalent frame method from 318.14 have been removed. Now, this is not because there's anything wrong with those methods. Those methods are completely valid. It's just that they are not used very often. Most of the time they're used primarily for preliminary sizing, but not for final design. And we looked at those, and we are trying to save paper when we print the code. And so what we did was we took those methods out, but we left references in the code that said, for instance, 821, the direct design method or the equivalent frame method, which have been removed, are valid. You just have to refer back to ACI 318.14 for the rules about how to use them. They aren't eliminated. They are just not printed in the current edition of the code, because we found that in practice, they actually weren't being used very often, but there's nothing wrong with those. So that same provision appears in section 6241. So those methods are still available. Here's a very important one, especially if you're doing commercial design of multi-story buildings. We all know that the mechanical engineers want to put holes at the worst possible locations in the structures that we design. That is right next to columns. They want to put holes through the slabs where the pipes come and conduits come down the columns. And so there are rules in ACI 318 about how to evaluate the punching shear strength of a slab intersecting a column. So a very common form of construction is flat slabs without any drop panels or shear caps, just a flat slab intersecting a column. And in order to evaluate punching shear strength, we need to account for those openings. And you see in the illustrations on the right, it describes how this is done for various situations, shapes of holes, and so on, how to evaluate that green dashed line, which is the perimeter of the punching shear zone. A big change is that it was determined that previously in 318.14 that the distance from the column that a opening may be located without affecting the strength of the column, punching shear strength, was 10 times H, where H is the thickness of the slab. And that created more situations where it was harder to design for openings like those shown on the right. That has been revised to 4H, so it's much smaller. That is, openings can be within or no closer than 4H from the column, but they and then they won't count against the punching shear strength. So this is a significant change, and I think makes life easier for engineers designing flat plate structures. Another change is that it was determined that for very thick slabs, so this figure shows actually an actual concrete slab in a building in the United States that was 2 feet thick, which is about 300 millimeters, I think. So it's quite thick. It had many stories of structure built above it, but this was the base of these upper floors. And it was noticed, or there was a near failure because the punching shear crack, as shown here, formed and moved out and did not intersect the top reinforcement that was there for preventing partially the reason that reinforcement is there to prevent punching shear. But this only occurs under the ACI design rules for very thick slabs. And so the rules have been changed slightly to prevent this situation occurring. And what we see on the top figure here on the right is the normal situation with a slab that is, no more than 150 millimeters thick, perhaps. And but for very thick slabs, it happens that we need to extend those top bars, as shown in the lower figure. So there's been a new rule added that those bars need to extend out at least 5D, where D is the effective thickness of the slab. It's not H, it's D. D is the distance from the surface to the centroid of the tension reinforcement. So this is a new rule. If you're dealing with a very thick slab and you're concerned about punching shear, make sure that you evaluate the extension of those bars and that they meet the 5D extension rule. Notice one thing that's very important is that extension is from the face of the column, as shown in both diagrams. That extension is not from the center line of the column, but from the face of the column. It's easy for the steel reinforcement supplier to mistakenly provide bars that are where their length is measured or extension is measured from the center of the column. It's from the face of the column that that extension is required. Okay, now post-tensioning. This is post-tensioning is a method that is widely used, particularly in the Western United States, not as much in the Eastern US. And I'm sure that in your career you will encounter it. You may commonly work with it, or it may be less common in the kind of work you do. But there are a few changes there. There is a new requirement for the spacing of non-pre-stressed reinforcement. So this is the normal deformed bars that are in the slab. And that spacing of that reinforcement, which is not the spacing of the post-tensioning tendon, but the spacing of the normal deformed reinforcement, has been reduced, and it is the same now as it is for non-pre-stressed or normally reinforced slabs. So actually things have been simplified a little bit, that spacing is the same. So the maximum spacing of deformed bars in pre-stressed slabs is now the same as for non-pre-stressed slabs. There is a requirement for something we call hairpin bars, as shown on the right, and backup bars. These are needed for post-tension anchorage zones. So what's shown in the bottom two figures is the anchorage or reaction zone for the post-tensioning cable or tendon. And we have found that for when there are several anchors close to each other in plan, spaced out along the edge of the slab, that we need, in some cases, backup bars, as shown there with the two black dots in the left figure. And sometimes we need, for thicker slabs, we need what are called anchor bars and hairpin bars. Now, why are we requiring these bars? It's been found that the slab can split under the pressure or the force of the post-tensioning tendons if there's insufficient reinforcement to inhibit this splitting and bursting of the edge of the slab. So these are new rules. If you're involved with this kind of construction, I would recommend that you review the rules for these backup bars, anchor bars, and hairpin bars. Okay, now walls. What I'll be talking about here are not seismic shear walls, but non-seismic walls. And there's a few changes. One of them is that cantilever retaining walls, there's a few illustrations there of loads on cantilevered earth retaining walls, are now moved into the chapter 13, or are designed according to chapter 13. Now, you might wonder, why is this? They're a wall. They were in the wall chapter, chapter 11, and now they have been referred to chapter 13, foundations. What we found is that in 318.14, as shown in the lower part of the slide, that there was some confusion about the reinforcement of retaining walls. Specifically, there were rules about a portion of the reinforcement that had to be on one face of the wall and the portion that had to be on the other. They weren't very clear they weren't very well understood. The definition of interior face and exterior face was not very clear. And we found that there really was not a strong technical basis for the 1/2, 2/3 rule. So now the rule is that there are 2 layers of bars near each face. It doesn't specify what the proportions are, as long as the calculations work for strength. And there is one exception where that is not required for walls greater than 10 inches thick. So that would be about 250 millimeters thick. And that is for single-story basement walls. Generally, these are found, at least in the US, in residences, so 1 story below ground. Those do not require 2 layers of reinforcement, but all other walls greater than 250 millimeters require 2 layers of reinforcement. Now let's talk about foundations. There are some really significant changes about foundations that I want to go over. As I mentioned, we moved the cantilevering wall provisions or design rules into the foundations chapter, and there have been many changes in the sections on the design of deep foundations. So what are deep foundations? Those are piles, drilled piers, drilled shafts, cased shafts, both cast in place and driven piles. They're all the types of foundations that are used in soft soil conditions. And I'll describe why those have changed in a moment. But I also want to note that there have been small changes in the minimum concrete strength required for different types of foundations, and also a change in the concrete cover requirement, meaning the thickness of concrete covering the reinforcement. So first of all, cantilever retaining walls. In 2014, the code described cantilever retaining walls as walls and that they should be designed as walls. In 2019, we had a philosophical change so that these cantilever retaining walls are actually designed according to the rules for a concrete slab. We believe that they perform better, are more economical, and it makes more sense to design them according to the rules for concrete slabs rather than walls. And I won't go into all of the details, but if you look on this chart, you will see that if we design cantilever retaining walls as a slab, as a one-way slab, then the rules for design get much simpler. And in general, that results in a more economical design because it's a little more reinforcement, but it's the same in both the vertical and the horizontal directions. So it's much easier to put into place. It also avoids having in the field, having the wrong reinforcement put vertically versus horizontal. They're the same. And so this chart outlines the differences between 318, 14, and 19. And if you're interested in that, you can refer to the sections shown there. I think you'll find it is an improvement over the last edition of the code. Now, regarding deep foundations, I said that I would explain why there have been changes in all these different types of foundation provisions. The code, the ACI code, mainly addresses deep foundation design for earthquake-resistant structures. In the US, the earthquake-resistant structures are designed according to a seismic design category, that's SDC, seismic design category, with category A being virtually no earthquake considerations for design, and categories D, E, and F being the most severe earthquake conditions for design. ACI 318 addresses deep foundation design for seismic conditions in these higher seismic zones, or design categories C, D, E, and F. So it's a subset of the overall requirements for designing deep foundations, but a very important set of conditions. Now, the situation that existed and still exists to some extent in the US is that there are rules for designing deep foundations in the ASCE 7 code, which is mainly a code about loads. There are different and sometimes conflicting rules in the International Building Code, which is the main governing building code in the US. And there are other, sometimes different and sometimes conflicting or inconsistent rules in ACI 318. So what we did was we took all of those rules from those three different major documents, and we put them into a funnel here, as is illustrated, and we put them all together, we sorted them out, debated them, and came up with one set of rules, which is in 318.19. So you will find a brand new set of revised rules for deep foundations in ACI 318.19. We are still working on getting all of the provisions moved out of ASCE 7 and IBC into ACI 318, but we've made a lot of progress. And the goal is to have the design provisions for earthquake design of high seismic deep foundations all be within one document and be consistent, and that would be ACI 318. So perhaps we'll get there in the 2025 edition. We're going to try. Now, I'm not going to go through in detail what all these changes are, because that would take maybe over an hour just to go through all those changes. So I'm just alerting you that if you're designing deep foundations for seismic conditions using ACI 318, you should go look in the foundations chapter and determine if there have been changes in the ACI 318 rules for that type of deep foundation as you go through your design. So this is not the detail of what these changes are, but it's letting you know that there have been changes. Okay, anchorage to concrete is everyone's favorite subject. When we reorganized the ACI code in 2014, it was a major reorganization. We reorganized all of the chapters except for the chapter on anchorage to concrete, which is chapter 17. And so we decided to leave that alone because there had been some major changes in the previous edition, and we didn't want to go and change it again. But when it came to the 2019 edition, we worked on reorganizing chapter 17 so that it looked similar to other chapters that had been reorganized in 2014. So it looks different. The provisions are generally the same. There haven't been major changes in the anchorage to concrete provisions, but we did add two more types of anchors, which I think are very interesting. One of those is screw anchors. So these are anchors where you drill a dry hole and then install the anchor, which has threads, steel threads, which cut into the concrete. You're probably familiar with these, but this is what is meant by screw anchors. They're very, very useful kind of anchor, fairly easy to install. I like them a lot. They may not work as well in corrosive conditions, but for protected conditions, they're nice. And then we added something on shear lugs. So what are shear lugs? On the left here, first of all, you see a screw anchor, post-installed screw anchor. So a hole is drilled, and that is inserted with an impact driving driver, wrench. And then shear lugs are the steel projections at the beneath base plates that project into the concrete foundation and provide additional shear capacity beyond the shear V there, beyond what could be provided by the dowel action of the anchor bolts, the 4 anchor bolts in this case shown in the lower diagram. And in the upper right, you see the one of these shear lug configurations. A lot of testing has been done on shear lugs. We didn't really know what their shear capacity was until fairly recently, at least reliably be able to predict that. So now there are rules in ACI 318 about how to design shear lugs. So we've kind of gained more confidence in how to design and what the shear capacity of column base plates with shear lugs are. Okay, now seismic, a very important topic. I have been involved in seismic design for more than 30 years now, and it never gets old. It's always changing. There's always new things to discover. And in the 318.19 code, we have made some changes in the seismic design provisions. If you would like a complete and very detailed tour of all of these seismic updates, I suggest that you find 2 articles in Concrete International. They were actually published last year in March and April. S.K. Ghosh and I wrote those together. They cover just about every detailed aspect of the changes to seismic design that occurred in the 2019 code. So I invite you to look at those, but I'm going to point out some of the changes that are most important in this presentation. Perhaps one of the biggest and most important changes is that higher strength reinforcement is now permitted in seismic design. Previously, we had grade 60 reinforcement, which is, what is that, 420 megapascal reinforcement was permitted for ductile seismic design, for flexural elements, and for shear. Now, 550 megapascal and even 690 megapascal reinforcement is permitted under certain conditions in seismic systems. The idea is that we should be able to reduce the congestion, the crowding of reinforcement if we're using higher strength reinforcement. Of course, what's going to happen is that the architect is going to say, oh, you can make all the columns smaller now, right? And the walls thinner because the reinforcement isn't as large. So it'll still be crowded. But anyway, this is now available to you, these higher strength reinforcements for different applications. And this table shown on the right, it's a little small, but you could look at it in the code. Table 20.2.2.4a shows what grades of reinforcement can be used in different applications. The table I've shown here is the inch-pound version of the table. Of course, if you look in the metric or the SI version of the ACI 318 code, you'll see these perhaps in more familiar units. But what you see here is everything in green is what's new or what's been changed. And you see that there are a lot of 80 and 100 KSI or 550 and 690 megapascal grades of steel allowed in different applications. So you may find this useful. for design in perhaps reducing costs, if you're able to reduce the total weight of reinforcement, perhaps reducing congestion of reinforcement or crowding of reinforcement, and perhaps in making elements thinner or smaller. It gives you more options, let's put it that way. Now, as far as when or if these different grades of reinforcement are available from steel mills, that's a very local question, and you would need to verify the availability of some of these grades where you're working in your project location. And in fact, in the US, it's not always easy to get some of these grades. For instance, the 690 megapascal grade is a little difficult to find because currently not a lot of that is used. Okay, so those are some new things related to seismic design with higher strength reinforcement. Now let's talk about seismic design of some specific earthquake force resisting systems. A lot of the changes have to do with the availability now of higher strength reinforcement for design. And what I've done is on these next few slides, I've shown where in the green box, where the new availability of steel grades is permitting you to use a different type of bar. So new in 2019 is using grade 80 or 550 megapascal reinforcement, in this case for flexural reinforcements in special moment frame beams. So anything in green on these slides is new in 2019. So I won't go into the detail here, but as you can see, as I go to some of these other illustrations, you see that for instance, the shear reinforcement now can be a higher grade, but also notice that the spacing of the reinforcement is reduced for the shear reinforcement to a smaller spacing, and there's a couple technical reasons for that, but it mainly has to do with the tendency of bars, especially in seismic applications, to buckle laterally between the points of support, which in this case are the shear reinforcement, the hoops in this case, in special moment frame beams. So just be aware, if you're using the higher grade reinforcement in certain applications, sometimes the spacing has changed, decreased slightly. We see here that, again, there's a spacing change if you're using 550 megapascal hoops in intermediate moment frames in this example. If we look then at columns in special moment frames, again, you can use the higher grade reinforcement, but the spacing has changed, has decreased slightly for the higher grade. And then we get to special structural walls. Now, this is probably where the most significant changes have occurred, and I'll try to cover the main points so that you understand what has changed in 2019 with special structural concrete shear walls for seismic. Here is a brief summary of the changes in shear walls, special structural walls, and I'll describe each of these briefly, but in subsequent slides. But the cutoff or the stopping of longitudinal bars, the rules have changed, I think, for the better. Reinforcement ratios at the ends of the walls have been changed somewhat. It probably won't affect in practice too much. It won't affect too many buildings. The shear demand is a very significant change that I'll be spending some time on. That is, the shear load that is required to be resisted by the walls has changed. There is a new drift capacity check, which again, probably not influence the design of walls very much. There are very significant changes in the detailing requirements, the hoops and cross ties in the special boundary elements at the ends of special walls. And there is a new section on ductile coupled walls. So I'll go through all of these briefly in the following slides. So previously in 2014, if you had a vertical wall, a vertical bar in a shear wall, and you got to a certain height in the building where you no longer needed that bar because the flexural demands have decreased as you go higher in the building, and you want to stop that bar, you had to, under the old rules, extend that bar 0.8 times the length, the horizontal length of the wall. So if you had, for example, a 10-meter long wall, which is fairly common in the US on the West Coast, if your shear wall was 10 meters wide this way, and you needed to stop a bar, you couldn't stop it where you no longer needed it. You needed to extend it 8 meters beyond that point. So 8 meters is more than, or is about 2 stories typically. So what was required was to extend these bars 2 stories above where they're needed, which in some cases, which is really excessive. And there actually wasn't a really solid technical reason to do that. So we had a lot of debate about that provision. And the new rule is illustrated here. Once you find the point at which a bar is no longer needed, you need to extend it at least 12 feet or a little less than 4 meters, like about 3.8 meters above the point that it's last needed, which is much much easier to build. And however, if that bar, that 3.8 meter extension went above the next floor, then you only need to go L sub D, so one tension development length above the next floor. So it could be actually significantly shorter than 12 feet. So this is a big change from the 0.8 times the length of the wall extension that was required. And this took a lot of debate and discussion and voting to get this change through. Okay, moving on to a different topic about walls. There is a new provision, which I have to say is a little bit controversial, regarding the location of lap splices. So lap splices are where 2 bars are joined by overlapping them like this. Lap splices are not permitted now in 318.19 in the zones shown in orange on the right. And those zones are at the base of a wall where a plastic hinge, an inelastic hinge will form. And it's in the special boundary regions. So these are the heavily reinforced regions near the ends of walls or at the intersections of walls, as shown on the left illustration, where there's a T-shaped wall and the boundary regions are shaded in orange. So within those boundary regions, over a distance from the height of the first story above the base, or one development length of those longitudinal bars below, lap splices are not permitted. So unfortunately, lap splices at that location are the simplest thing the simplest way to construct those walls. Obviously, you have short bars coming out of the foundation, and then you continue to build the wall above, and that's the easiest way to do it. The problem has to do with the inelastic stretching of bars in that region. If only one or two cracks form right at the top of the foundation as the wall flexes back and forth. All of the strain in those bars will end up in the in a very concentrated region, short region, and it could lead to fracture of the bars. So based on research and examination of various studies, the rule was implemented to prohibit lap splices in the orange zones shown here. Now, instead of lap splices, it's possible to use mechanical couplers. And there are, of course, at least 6 or 10 different types of mechanical couplers available on the market. It's recognized that they are more expensive than lap splices. They can be difficult to install, but we felt that it's very important to focus on good ductile inelastic behavior at this particular location in shear walls. So that's the background on that change. Another change, which maybe is a little harder to understand, but it makes sense, is when the longitudinal or the vertical flexural reinforcement in a wall is adequate for flexure, but is not adequate to create many small cracks, horizontal cracks up the wall, height of the wall. Again, that concentrates inelastic strains in just a few locations, which could promote fracture of the bar. This was based on observations from earthquakes in Chile and New Zealand, Christchurch, that only 1 or 2 large cracks formed in some walls and not very many small secondary cracks. It's just not a good situation as illustrated by the analysis results shown on the right. So by adding a little more reinforcement in the ends of the walls, we end up with a situation as illustrated here, where there are many small horizontal cracks. The inelastic strain in the vertical or longitudinal bars is distributed well over the height of the wall, and there's less possibility of a strain concentration and a fracture. So immediately you're wondering, well, how much more reinforcement do I need to put in the ends of the walls? There's almost no room in there as it is under the current ACI provisions. Well, this new ratio is 6 times the square root of F prime C over Fy. I think it's actually different for SI units. This is in inch-pounds units. I forgot to mention, in both the SI and inch-pound units of the code, there is a table in Appendix C that shows every equation in the code in both inch-pound units and SI units. So if you're ever looking at an inch-pound equation and you want to know how to calculate it, how to evaluate that expression in SI units, look in Appendix C and you'll find it there. So for instance, there's a different equation for this row for SI units. In any case, this amount of reinforcement needs to be near the ends of the walls. And that results in this much better behavior as illustrated here. Now, let me back up, I'm sorry. You will find, if you're designing walls with this new rule, that in most cases, it doesn't change the amount of reinforcement. If it does change the amount of reinforcement, it's by a small amount. So this is not a big impact. It's just designed to try to improve ductile behavior of walls in a few situations. All right, another really big change is this shear amplification. So just a little bit of background on this, particularly for tall buildings. By that, I mean 15 stories or taller, maybe up to 50 or more stories. In the US, we design those tall buildings, of course, according to the code, But we also generally require in the Western US a review by another engineer called peer review, P-E-E-R, peer review, to evaluate our analysis methods. And I think it's a good system. It provides very consistent levels of design. But when we do that kind of design, now it is pretty much universal practice to perform a nonlinear time history or response history analysis. So we model the structure, this tall structure, we subject it to the accelerations of an actual or recorded earthquake, and we evaluate the response, particularly the inelastic behavior. And we do that for a number of earthquakes, either 7 or 11 different earthquakes for design of the tall building. And what we have always found for the past 15 or 20 years is that the shear in the tall walls is always greater than what you would find if you just applied the ACI 318 code provisions for shorter buildings, and that it is necessary to provide more shear reinforcement in those tall walls than would be determined through a sort of a more basic type of analysis. So we have known that the shear demand or the shear loads in tall walls is significantly greater than what the code would tell us for tall buildings. So in this equation, what you see here, V sub U is what you would get from regular linear analysis using code-based provisions. And we find that if you are not going to perform the kind of analysis that I described, the response history or time history nonlinear analysis, that you need to apply these amplification factors to shear only. This isn't for moment, it's just for shear in the walls. And those amplification factors are large omega sub V and small omega sub V. So as I said, V sub U is the shear obtained from the code lateral load analysis with factored load combinations, but assuming a linear structure. Large omega sub V is an increase in shear design force related to the overstrength of the walls. So when a plastic hinge forms, the shear that's generated through formation of that plastic hinge is higher than the sort of idealized version. And that overstrength factor is greater than 1, and it increases the shear in the wall. The other omega sub V is a small omega sub V. This comes from the dynamic analysis showing that higher frequency modes in the structure for tall structures increase the shear demand in the walls. So these are two known effects that are now in the code. But the combination of those two factors is less than or equal to 3. So there's a cap. But notice that a building previously designed according to linear analysis, tall building using V sub U may now require design for as much as 3 times V sub U for shear only. This is not for overturning or for moment. So this is somewhat of a shock to us in the design community. It's less of a shock for consultants who have been designing tall buildings for the last 20 years or so using this nonlinear analysis. So we know, because we've accounted for these effects already in our designs for the last 20 years or so, that we have included this effect, but now we're putting this effect into the code to make sure that it's considered in all designs. Here is the way of calculating large omega sub V, so that's the overstrength factor. It has to do with the strength of concrete and the strength of reinforcement being greater than what is specified. And that factor can be 1.5, depending on the height of the wall, divided by the length of the wall. And I won't go into the details here, but that factor is 1 or greater, depending on the slenderness of the wall and the applied load and the plastic hinge moment. And then the small omega sub v is really height dependent. And this n sub s is the number of stories, n sub s. And so we see that for taller buildings, this factor increases. It begins at 1.0 and it increases as high as 1.8. But once again, the multiplying large omega and small omega together, the combination does not have to be greater than 3. I want to point out that this equation, again, is in inch-pound units. This n sub s is greater than or equal to 0.007 h sub WCS. That's height of the wall above the critical section that you're designing for. And it is in inches. So you need to use the appropriate equation for SI units if you're evaluating that equation. Okay. This next provision related to walls, it's presented here as a deformation demand check. So a check that your wall can deform adequately and not exhibit bad behavior when it's called upon to bend in an earthquake. What it really is something that affects the wall thickness. It's really a check to make sure that the wall is thick enough that it doesn't buckle out of plane, that is, buckle sideways, when it's subjected to high seismic loads that are also cause inelastic action. So in these equations, in equation 2, the lowercase b, that's the thickness of the wall. B is how thick the wall is. And the simple check to make sure that the wall is thick enough to prevent this out of plane failure is shown in equation 2. That's kind of a conservative check, meaning you might be able to get a thinner wall if you follow the second or the third expression, number 3 there. However, as you can see, there are some parameters in that expression for item 3, which you don't know before you complete design of the wall. So it's, to use equation 3, it's an iterative process. You have to go around. And we provided equation 2 so that in preliminary design and even in final design, you can just establish what the minimum wall thickness is and not worry about iterating through what the length of the wall is, the seismic demands, V sub E, the area of concrete, A sub CV, and so on, that you just use the simpler expression. So for preliminary sizing and even for final design, you can use the minimum wall thickness check shown in item 2. And now there have been some other changes in the detailing requirements for special walls, which are important and, again, controversial. There was not uniform agreement in the committees, the seismic subcommittee and the main committee, on whether these requirements were needed or not. But through the consensus process and through voting and through revision and debate, we developed the detailing provisions, which I'm about to show you. You will see that they increase the difficulty of construction significantly. And that's why these are even now, currently in debate within ACI 318. We may issue clarification of these provisions that I'm about to show you that may make them a little easier to comply with. But I'll show you what they are now as published in ACI 318-19. And if and when there is a revision, not a revision, but a clarification and interpretation of those provisions, that will come out, I'm guessing within the next, probably within the next 6 months, but I can't be certain. We're working on that though. Okay, so what are these provisions? All of the bars within the special boundary zone, as shown in the gray area, all of the vertical bars have to be enclosed by either a 135-degree seismic hook or a 90-degree bend. So you see in this illustration that every black circle is enclosed or constrained by either a 90-degree corner or a 135-degree hook. This is different from 318.14, where, for instance, the orange bars shown there, the orange-colored bars, were permitted to use a 90-degree hook on one end and a 135-degree hook on the other end. And this was made construction not easy, but possible. Putting 135-degree hooks on both ends of cross ties definitely makes life more difficult for a contractor. I won't comment any further on that other than to say we are evaluating these requirements now. It's very difficult to build this way. The other requirement is that there be closed hoops that are no longer than 2 times the thickness of the wall, and that when those closed hoops are installed, that they overlap as shown here. There's a blue closed hoop on the left and a black closed hoop on the right. Again, this is a difficult detail to construct. I suspect that the best way to construct these would be to pre-assemble these reinforcement cages and thread in the bars into their locations. But I'm not a contractor, so I can't predict what the best way to do this is, but it will be a big change. And then the other thing to notice is the orange bars on the right, where it's labeled longitudinal web reinforcement. Those are also required to have 135-degree hooks on each end within the plastic hinge region. So not everywhere in the wall, but in the area where we believe yielding would occur. Again, these are difficult to install. Sure, there may be some inventive entrepreneur out there who's going to figure out how to do this. But I'm sorry to be the messenger of a more difficult method of construction, but the test data from laboratory tests indicated that to get sufficient confinement of the concrete at the ends of walls, this needed to be the case. So it's an ongoing topic of discussion, though. Yeah, so I already described this. This is the orange bars on the right. So I've described all the changes there in reinforcement detailing for special structural walls. Okay, moving on to a different topic related to walls is I think we're all familiar with this type of walls shown here on the right, where there are 2 solid shear walls and they are connected by coupling beams, and that's called a ductile coupled wall. And many thousands, probably hundreds of thousands of these kinds of walls have been constructed around the world. Popular in the US, they're a very efficient use of concrete, and they allow openings for corridors and windows and so on, stairways. but they have never been defined in the code. They're a very common and popular type of shear wall that has never been defined. We all know what it is, but there's no official definition. So we now have an official definition of a ductile coupled shear wall. It's given in the code in section 18.10.9, and it has to do with the height to length ratio of the wall being greater than 2, and with the provision of coupling beams and what their length to height ratio is as well. Now you may ask, why is it important that we define what a ductile coupled wall is? It's important because, at least in the US, when we design for seismic loads, for each structural system, whether it's a steel moment frame, concrete moment frame, concrete shear wall, steel plate shear wall, whatever, there is a factor called R. R is to account for the inelastic effects of the design, and R is a reduction factor. That is, we divide the calculated elastic load by R to come up with the design load. I believe there's something similar in your code, but around the world, these factors take different forms, but they have a similar purpose. So in the US, we have an R factor, and we divide the elastic seismic loads by R to obtain the design loads for seismic. There has never been a defined R factor for ductile coupled walls. And in order to define that, we had to define the walls. So now, since we have a defined ductile coupled wall, we now have in ASCE 7, we have a defined R factor for a ductile coupled wall. And the good news is that that R factor is quite high. The highest R factor that we use for any structural system in the US is 8. Many R factors are down around 3, 4, 5, in the 4, 5, maybe 6 range. But for certain systems that are very good, very ductile, reliable systems, we use an R factor of 8. And we have assigned an R factor of 8 to this type of structure. So that's good news. It helps us be more confident in and design more economically this type of wall. Okay, now we're going to talk a little bit about seismic foundation issues. I already showed you this slide where I mentioned that we tried to combine all of the deep foundation seismic provisions for high seismic zones into one list of provisions in ACI 318.19. We didn't quite get there, but I think we will completely in the next version of the code. What are deep foundations that are affected here? I've shown some examples: uncased or unenclosed, cast in place concrete drilled or augured piles. So metal cased concrete piles, so a pipe pile with concrete in the middle. Also, metal cased is slightly different from a concrete filled pipe pile, and precast concrete piles. So I believe probably all of these foundation types are common in the areas where you work, and so you may be interested in the revised seismic provisions in ACI 318 for these types of deep foundations. But I did mention that we don't include in this presentation all of those changes because they're very numerous, and it's best if you just look at the particular type of deep foundation that you're considering. Okay, we're getting near the end here. I wanted to talk briefly about what we might expect in the next edition of code, which will be 2025. A big concern worldwide, as we all know, is the addition of carbon to the atmosphere. And unfortunately, the production of cement around the world contributes to a large percentage of the carbon in the atmosphere. This quotation is from a study in, I think, 2016. More recent studies estimate that the production of cement may be responsible for as much as 8% of the CO2 that's put in by people into the atmosphere every year. So it is a big problem. And as engineers, we're smart people. We can perhaps have some influence on this. So what we did in preparing the 2025 edition of the code is we have created a special subcommittee called Sustainability. And that subcommittee is working on sustainability provisions for ACI 31825. And those provisions will go in an appendix. So an appendix of the code contains provisions that are optional. If you're working on a project and the owner, perhaps it's a government project or an owner that has particular objectives regarding environmental effects of construction, if your project has environmental or sustainability requirements, the project can use Appendix N as guidance for creating a more sustainable structure. They aren't requirements that are in the main part of the code, but they're optional and can be used. So the subcommittee is working on this currently. This appendix will have a section that outlines the scope and purpose of the appendix, but more importantly, it will explain how the sustainability properties of a particular concrete mixture are to be determined. So what we need is, if we're going to compare concrete mixes and with different ingredients, different amounts of cement, and so on, we need to compare them on a consistent basis. So that's what this section 2 defines, is how to evaluate the sustainability aspects of a particular concrete. And then similarly, there are ways to measure the overall sustainability impacts of an overall structural system. So a concrete system, maybe it's a precast system or a flat plate with column system, many possible different options. But if we're going to compare how the environmental impacts between all these different systems, or even with wood systems or steel systems, and you want to compare them, this section will describe how to do that for concrete systems so that we're comparing everything on a consistent basis. And then there is an aspect of sustainability, which is resiliency. So sustainability has to do with what are the environmental impacts of designing, constructing, and using a structure that is made out of concrete. Resiliency is related to sustainability in that if we can make a structure more resilient, so resiliency means resistant to deterioration and extension of the life. So a structure with a long life is resilient. Then we've created a less impactful structure environmentally. So there is an aspect to sustainability, which is resiliency. And again, this appendix defines how resiliency should be evaluated. So this is an outline of what this appendix is going to be. Again, these will be optional requirements, but I just wanted to make you aware that they will be there. And if you have a project that requires certain sustainability measures, this is a good place to refer to for the concrete elements of the project. There is another appendix A, which was introduced in 31819, and it is about nonlinear response history analysis, the kind of analysis for seismic design that I mentioned earlier. And it is being updated. It was kind of an outline in its first version. There's more detail being added to it now. giving guidance and limitations on how this kind of analysis should be performed. And then chapter 17 for anchorage to concrete has been around now for a while, but there appears to be kind of a philosophical mismatch between the requirements for an anchor designed according to chapter 17 and the requirements for an embedded reinforcing bar. You know, if you look at them, they're basically doing the same thing. You're pulling out an anchor and you're pulling out a bar, but we design them very differently. So there is a committee working on, a subcommittee working on trying to bring together the provisions to make them consistent between anchors and development of reinforcement. I don't know what that subcommittee will ultimately produce, but it's working on that question now. Also, there's to be a new chapter on wind design called performance-based wind design. So you may be familiar with performance-based seismic design, where you set certain performance goals and then you design to meet those goals. More recently, in the US, the American Society of Civil Engineers has produced a pre-standard, so it's not a standard, but it's a preview of a potential future standard on performance-based design for wind loads as opposed to seismic loads. So ACI is supporting that change by developing an appendix to provide guidance on performance-based wind design. And this, of course, mainly applies to tall buildings. There have been revisions to the one-way shear capacity. In 2019, we introduced some revisions that were good. They helped unify and simplify shear design, but we discovered that there were some problems with those in that they required excessive amounts of reinforcement in tall cantilever shear walls, retaining walls, as shown on the left, very tall, like over 5 meters tall, and also somewhat increased the thickness of footings like the one shown on the right. So we're working on making corrections to that. And then regarding precast and pre-stressed concrete and post-tension concrete, due to some very long and complicated negotiations within the various technical societies in the US and trade organizations, ACI is now creating companion codes to 318 that are specifically for precast construction and for post-tension construction. And this diagram illustrates that there will be a new ACI 319 for precast construction and 320 for post-tension construction. And those are separate committees from although we coordinate very closely, as this diagram illustrates. We have subcommittees within 318 that are very closely linked with these other codes, so we stay coordinated. But just be aware that ACI plans to issue those codes in 2025. And I've already talked about foundations. We're trying to improve that coordination for deep foundation. And so here is the last slide. I talked about potential for future developments and also a main outline of the changes that will occur or that have occurred in 2019 and what we might expect in 2025. Finally, I would like to just...
finally, just to finish this off, I'd like to mention something that's just been released by ACI.
This is a recording. That's a recording. And thank you for your time. So I recorded this presentation for another venue, and those two... Anyway, I will just say that there's a version of ACI 318 that is has been launched by ACI, which is called ACI 318 Plus. It's an electronic version. It's really useful because you can search for things. You can search for words. Like if you want to search for, let's say, hoop, the word hoop, you can look and it will show you all the instances of hoop, and you can then end up with a full understanding of everywhere that hoop is mentioned, or composite. You could look up the word composite or composite beams or whatever. So I'll just mention that. And then finally, I'd like to thank you for your time. Hopefully I've helped you understand some of the changes, most of the most important changes in ACI 318.19 and what we might be looking at in 318.25. So I think I finished close to on time. And
thank you very much.
Yes, so thank you.
Dr. Andrew, for the very, very extensive presentation, although you said that there is actually a 6-hour version of it.
Yes.
That would be even more extensive. I'm sure most of us here would also love to hear the 6-hour version of this talk.
But it's more boring too.
Yeah.
It's more boring.
Okay, so we still have about 26 minutes for question and answers.
Okay.
And I would like to remind you that actually we will have, you can ask questions whether you're here or whether you are in our Zoom account. So actually this is also broadcasted via Zoom. So if you want to ask questions directly via Zoom, please raise your hands or chat. Or if you want to ask questions here, then just raise your hand, and then our kind assistants here will give the mic to you. Jadi buat Bapak Ibu sekalian yang ingin bertanya, pertanyaan ini tidak hanya untuk Bapak Ibu yang hadir di ruangan di Hotel Borobudur hari ini, tapi juga untuk yang berada di rumah, yang mendengarkan dari tempat-tempat tertentu, boleh langsung ketikkan pertanyaannya melalui chat box, nanti akan kita bacakan. Atau juga kalau misalnya ingin tampil di layar gitu ya, boleh juga mungkin raise hands, nanti akan kita tampilkan di Zoom begitu. Nah, silahkan Bapak Ibu sekalian, ada yang ingin bertanya? Is there a question from the room? Okay, directly, Pak Anien, silahkan.
I see there's also one question in the chat box, so we can get to that one also at some point.
Yeah, thank you very much for the moderator. Thank you very much also Andy for it. It was very nice presentation. Actually, I have only 3 simple questions. First is regarding the numbers of concrete tests specified in the ACI. According to my personal experience or opinion, considering the quality issue in Indonesia, it seems that numbers of the concrete sample test is a little bit too small. So what do you think on that issue?
Okay.
Second thing is, yes.
Would you like me to answer that question first?
Yeah, I think I have another
He
2.
has 3 questions.
Okay.
Yeah.
Do you want to hear them all, or do you want to?
Yes, please. Yeah,
Just
maybe all
simple
3.
Question,
and then
Andy, just
Okay.
simple question. The second thing is regarding the development length of the lower part of the column to the foundation. So please kindly more elaborate on that requirement, because we are Indonesia sometimes still arguing which one is the correct one. And the last one is the third is regarding the supplies of the main bar of the column at the lower part also. So again, there's one also some arguments on that one. So please kindly more elaborate on that issue.
Okay.
Thank you very much, Andy.
Yeah. Okay, so your first question was about the number of concrete strength tests required when testing concrete in the field during construction. And you noted that in recent versions of the ACI code, the number of required, I don't know, do you use cylinders or cubes in Indonesia? Cylinders, probably?
Cylinders. We are using...
Cylinders,
Hello?
okay.
Okay.
Yeah, okay. So the number of
course,
cylinders...
we use cylinder
yeah.
because following the current code, we have to use cylinder instead of cubic test.
I'm sorry, what was the last part?
Yeah, of course, the sample should be cylinder test instead of cubic test.
Okay, okay. So the number of tests in recent versions of ACI 318 has been required now is 2 instead of 3. It was 3 for decades, for a long time. That was based primarily on data gathered in the United States for the consistency and predictability of strength from cylinder tests. But it is definitely calibrated to the US situation in terms of concrete supply, quality control, so on and so forth. One thing to remember is that the building code is always the minimum standard, and the engineer can always specify more demanding or higher requirements. And particularly when you believe that local practice is different from, say, US practice, I would suggest that you could, in your project specifications, require testing of as many cylinders as you think is necessary. Typically it's been 3, but if you feel even more than that is required, I think it's entirely appropriate for the structural engineer to do that. So I don't know if that's practical. Perhaps contractors are resistant to testing any more cylinders than they have to because of the expense and time required and storing the samples and so on. But I just want to say, if you feel that you need better information about the consistency of concrete, that you should request it. And there's nothing in the code that says you can't test more than the minimum that's in the code. So that's the first question. The second is development length of column bars into the foundation. Is that right, I believe?
Yes, that's the question.
Okay. Now, is it the length that you are interested or the orientation of the hooks?
No, the development length to the foundation or to the parquet or to the basement floor.
Yes. So if those bars have hooks, then of course the development length for a hook is described in ACI 318, and I would recommend you use those hooks. Lengths. If you have straight bars, there are other development lengths for straight bars specified in the code, and I would recommend those. I'm not sure if perhaps you're having some disagreements perhaps with the contractor about what those development lengths should be, but that's what I would recommend. That's number 2, and we can have more discussion about these if you like. Number 3, splicing the main bars in columns. So I'm guessing that your question has to do with, can the lap splices be immediately above the concrete slab, or do they need to be up higher at mid-height of the column?
No, not that the
No?
question, but because some consultant here interpret the position of the splash, which is of course in the middle of the floor, is should be located in the not low at the lower part of the building, or it should be at the second floor, for example.
I see. It is possible to put splices at the lowest level, as long as they are long enough and confined well enough. I don't think there's rules in the code currently that would prohibit lap splices in columns in the lowest floor of the building. Is that what you're wondering?
Yes, but the current issue, very sorry to say, in Indonesia there are two opinions. First, regarding that it should be located at the second floor instead of the first floor. That's the first opinion. But the other consultant consider it's still okay. It is in the first floor, as long as as long as it's okay with, for example, the position of the splice above the L0 or etc. Also the confinement, of course, yeah.
Yeah. Well, I would be interested to hear what the reasoning is for moving or requiring the splice to be higher than for columns than the first floor. There are many different situations. I mean, we could be talking about moment frame columns or mainly gravity supporting columns. There are detailing requirements in the code that sometimes push the lap splices to the mid-height of the column instead of directly above the slab. And those are sometimes controversial as well. But as far as which story they're located in, it would be interesting to know what the rationale is for keeping the splices above, not on the lowest floor.
If possible, I can continue a little bit.
Yes.
Yeah, for number 1, yeah. That's become a big issue actually, Andy, because we will understand that the code is minimum requirement. Then the actual situation, then every consultant specify different numbers of the sample. That's the big problem for us. And then normally critical owner then complain, why you specify like that? Why the other consultant is not the same with you? That's the problem, Andy.
Yeah.
Okay.
I
Perhaps
think
it's a very interesting discussion. It would be very it would be very well elaborated later on. Hopefully,
Okay,
Andrew
no
can
problem.
have another
Okay.
session maybe
Please,
in
yeah,
more detail.
please.
So I would like to accommodate more questions actually,
Okay.
Andy, if that's allowed. So there are 2 questions on the chat, but also we want to give time to ask questions for the people here. So, but firstly, let me read the questions from the floor, from the Zoom. So there's a question here that from Pakisna, from PT Bukaka. The question is that when the ACI 318 updated and several terms changed, did ACI consider to the building that was previously built? How does it consider the old buildings already built?
Right.
Perhaps Andy can answer this.
That is a very good question. It's a question that comes up always. every time that a new code is developed, not just the ACI code, but other codes, the question comes up, well, from perhaps a building owner. See, I designed this building 5 years ago, and it seems I may be losing my connection here. But you designed this building for me 5 years ago, and now there's a new building code, and it's different. And what about my older building? So this is not a unique question to ACI, but it's a philosophical question for all building codes. I think at ACI, we have taken the position that we try to use the best available and latest research and experience and studies to re-examine the code every time we issue a new edition. Sometimes that results in more demanding or more higher requirements than older editions. In fact, if you looked at a copy of ACI 318 from 50 years ago, it would not be anything like the building designed then would not look anything like what it looks like today. So it's an incremental change. But it is a concern to particularly building owners and the general public and to government officials about, well, what about older buildings? Well, generally the changes from one code to the next are increments that are not big changes, and the more recent older buildings are still, they're not unsafe. They just may have they may be, for instance, damaged more in an earthquake than a newer building. But when a big change comes along, for instance, the one I described about the design shear force for tall concrete shear walls, you have to wonder, what about the existing shear walls? Well, fortunately for that particular case, for very tall shear walls, buildings, which are subject to earthquakes, most of those are in the Western United States. And for the last 20 years or more, we have been designing them in a way that reflects that change, that up to 3 times multiplier on shear that I described. So fortunately for that particular change, which is a big one, we aren't concerned about the older buildings because we already considered that. And so each change is, a debate. We try to make the most reasonable changes and make them not excessive. But this is the nature of building codes. So it's a very good question, and we could probably have a very long discussion about it.
Okay, thank you very much for the kind answer. Actually, I've been informed that later on there will be a session by Pak Davi and also Pak Iswandi, and then both of them will actually address this question further. Jadi pertanyaan mengenai gimana nih efeknya terhadap bangunan yang lama mungkin akan bisa di-address di sesi-sesi berikutnya. So stay tuned for the other sessions after this. So we still have a little bit more time. I think it would be nice to have 2 more questions, one from here and one from Zoom. So I see one person over there. Bisa dikasih ke sana. Itu tuh Mas. Oke.
Thank you. I have one question for Andy about the inclusion of size effect in the shear provision, because I think it's the first time in the ACI revision that you have included the size effect. could you elaborate to us about, let's say, the development process of this shear provision? Is there any influence from the European standard or even the Canadian standard to this? And my second question is, what is the implication for the design of the new structures with this size effect? For example, if we have a thick, rough foundation, for example, how should we deal with that, and how should we treat the existing one? Thank you very much.
Okay, thank you. Two very good questions. What you were referring to was in the revised one-way shear capacity or strength equations now, there have been introduced two factors. One is called a size effect, and the other is a flexural reinforcement effect. And those two factors influence the shear strength, the calculated shear strength of a section, whether it's a beam or a one-way slab or a footing or a cantilever retaining wall in one-way bending. So I think your question was primarily about the size effect, is that right?
Yeah. Hello? Can you hear us?
Yes.
Yes, my question is more related to the size effect. Could you elaborate to us how we end up with the provision that we have?
Okay. So the development process, let me just explain a little more background for the rest of the audience. So the size effect is a reduction in shear with the increase in the thickness of the element that is being evaluated. So the size effect for a beam, for example, and this factor is less than 1, begins to take effect at a beam depth of about 250. If you had a 500 millimeter deep beam, the shear stress that is allowed, or the shear strength, would be less than for the shallower beam. So the idea is that as a shear section becomes very large, it's proportionally its shear strength is reduced. And there's at least 2 and probably more theories about why that happens. But it's been observed in tests. It's been an idea that has been considered for many years, probably going back at least 20 years. The observation that in laboratory tests of very deep beams, the shear strength per unit area was less than for shallower beams or less deep beams. So in terms of the development, it's based on data. It's definitely a real effect. The question has been, what should that factor be? And should there be a way to bring that factor back to 1, perhaps by providing sufficient reinforcement and so on? During the 2019 code cycle, between 2014 and 2019, there was very significant debate and development and seminars and so on held by ACI 318 Subcommittee E, which deals with the strength, the moment strength, shear strength, torsional strength of concrete sections to develop a recommended size effect. So that was worked out based on data, experimental data, and through debate and about different types of data, different types of tests. And the current size effect factor that's there is based on that development process. I couldn't tell you the exact details of how it was developed, but it's based on experimental observations. The implications of the size effect are actually very significant. You mentioned a raft foundation, or sometimes we call it a mat foundation. Obviously, that's a very thick element, and the size effect factor becomes quite severe for a very deep element. It's much less than 1, requiring more shear reinforcement. We are currently developing a code interpretation and perhaps revised rules for very thick foundation elements. Subcommittees E and F. F is the foundation subcommittee, and E I mentioned was the shear moment and torsional strength subcommittee, are looking closely at the size effect for deep foundations. And we may put a cap or a limit on the size effect factor so that foundations like raft foundations, it doesn't become a very unreasonably low factor. So does that answer your question?
Yes,
Okay.
thank you very much, Andy. Thank you.
Thank you very much for the question. We have very limited time, but I see that there is one more question in Zoom, but perhaps this will be the last question for today, for the session, before we close it, if you're okay with that. So the last question is from Muhammad Fauzi Darmawan. How can we evaluate the floor vibration during the design process of a building? Can we assign constraint at all of the degree of freedoms except the vertical translation? Then we conduct model analysis to see the natural frequency of the slab. That's the question, Andy.
I'm so glad you asked this question, because I spend about 50% of my work is on floor vibrations. So, but there's a couple very specific elements in this question, and then there is a more general question. So I'll try to answer quickly because I know we're running out of time. But when looking at the design of a new building, and you want to understand the floor vibration characteristics, yes, a finite element model is a very good way to do that. A couple things you may wish to do is perhaps increase the expected concrete strength, F prime C in ACI terminology, by some amount, maybe 0.3 or 0.4, to account for the actual strength that you think will be in the changes the modulus of elasticity E, which will affect the vibration response. Thing you might want to do. But you also noted that the fixing the vertical translation mode of a floor. So typically what we do is model an entire floor plate. We do fix the vertical translation at each column or wall, and then perform a modal analysis to get the natural frequencies. And that tells you a lot about the slab, the floor. I will also say, though, that there are even better finite element methods available that have to do with modal superposition. And I don't want to create an advertisement, but I will say that what I have used is the software RAM Concept, which analyzes concrete floors. And the very nice thing about RAM Concept, and the only reason I'm mentioning it, it is the only widely available software that I know of that will perform this modal superposition analysis, which is, I think, far superior to some other methods. So I'm not advertising that software. I just want to mention that this method, and if you do research into, say, the user's manual for Concept, you'll see the references to the original research that was done to develop the method. And you might want to explore that. I think it's probably the best way to analyze floor vibrations.
Okay, thank you very much, Andy, for the kind answer. I hope it answers your question. So perhaps with this, I would like to close the session today with Andrew Taylor. Please give a big applause for him. And I will return the mic back to our MC, Ibu Dini.
Thank you.
Ya, terima kasih Ibu Prasanti, and thank you for Mr. Taylor. Bapak dan Ibu, kita akan waktunya break selama 15 menit. Kami persilahkan Bapak untuk menikmati kopi dan teh serta makanan yang telah disediakan. Kita akan kembali lagi pada pukul 10.45. Untuk itu kami